Now that we spent a lot of time going through problem 3 in detail, we'll move a little bit faster through problem 4, even though it's a more complicated circuit. In problem 3, you were asked to find the voltage across the capacitor, which, like the current through an inductor, is the first thing you'd need to find no matter what. In problem 4, the question is to find the voltage across the inductor. And let's say the voltage across the inductor for all time greater than or equal to 0. So, first step, as always, is to draw for time less than 0. Actually, the first step is just to double check that this is a system that is switched DC first order. It's first order because it's just got one energy storage component, and it is switched DC because before time equals 0, it's one set of DC values. After time equals 0, a separate set of DC values are switched in. So our first step, as always, is to draw it for time less than 0. And the goal is to find, we want to find VL, right? No, we always find either the voltage across the capacitor or that current through the inductor. And that's going to be our, I think we usually use the form capital I L naught. So let's draw it for time less than 0. Is the switch open or closed? Well, it opens for time less than 0. So therefore, for time less than 0, it must be closed. Got our 5. Our inductor, since we're in DC steady state, looks like a short. And this, for time less than 0, 10 U of t. U of t for time less than 0 is 0, and a 0. So this becomes a 0 volt voltage source. And a 0 volt voltage source is more simply drawn just as a wire. Okay, already we're stuck because our goal is to find IL naught, and there's no IL naught in this. So we have to go back to our original diagram and define IL naught. Now, since we've defined VL here in this way with plus on the top, we really have to define IL naught in this direction to make it agree with, that's our current through our inductor. I'll just simply say I. That's our current through the inductor. So it's leaving at the more negative and entering in the more positive. So that's passive sign convention as it should be. So this is what we want to find. This is our IL naught. It's kind of an odd looking thing, isn't it? I think if I was to redraw this, maybe you guys can see it already, but it might be more helpful to redraw this. All I did was move that 4 around on the side. And I hope it's clear from the way that I drew it that this is like a 0 ohm resistor in parallel with a 4 ohm resistor. So that would have a total impedance of 0 ohms. Now we can't combine them because if we did, we would destroy all of our internal currents. And after all, that's what we want to find is our internal currents. But it is clear that all the current is going to go through this short, and none of it, when faced with a choice between going through a short or the 4 ohm, would go through the 4 ohm. It's really just a current divider. We could do a Norton equivalent of this, a source transform, and we'd see there's some current going through here. All of it would go through the short. And so this 10 volts is just seeing this 5 ohm resistance, and that's it. And so therefore IL naught is going to be our 10 volts over our 5 ohms or 2 amps. And that's our initial condition. Next step, draw for time greater than 0, and our goal is to find tau. So for time greater than 0, this switch opens up. That means if there's no current flowing through this side, there can be no current flowing through this wire, right? We could have drawn if this switch is open, we can draw a big node around here. The sum of all the currents exiting the node has to be 0. Well, there's no current here. That means this current plus nothing has to equal 0. So therefore, this current is 0. Since we're not interested in anything on this side, we're only interested on this part. In particular, we're interested in the equivalent resistance that this inductor sees. We can ignore this and not draw it. If we were instead interested in this, if the inductor was on this side, we'd have to draw this side. So what we have here is a inductor, and now it actually is an inductor. And we want to know what kind of current's going through it, because we're always interested in the current through the inductor, no matter what we've been asked to find. Now, for time greater than 0, this turns on. U of t for time greater than 0 is 1. So that's 10 times 1, or just a 10-volt source. And when we want to find impedances, the impedance that this inductor sees, we zero all of our independent sources. So the question is, if we were to think about from the inductor standpoint, we're not opening the inductor, but we're asking if we're forcing current through this thing and sucking it out of here, how much impedance do we see? So we always zero voltage sources, and we always zero current sources as well. We zero all of our independent sources. And when we zero them, a 0-volt voltage source looks like a short. And it's pretty clear that that inductor here just sees 4 ohms. So therefore, the R equivalent is 4 ohms. And our tau, which for a capacitive circuit would be RC, but for an inductive circuit is L over R, is for this 1 Henry over 4 ohms, which is 1/4. So that is our goal for step 2. Step 3. Step 3, we want to draw it at time equals infinity. And our goal is to find our I sub L of infinity. Even though we're asked to find V sub L, we're always interested in finding the I sub L or the V sub C first. So at time equals infinity, this is open. And so the only part of our circuit that's left is the stuff to the right. We don't even have to draw the 5 because no current goes through the 5, right? It can't go through this open. And since we're only interested on the inductor side, the 5 does not contribute to that at all. Now, this is DC steady state. We're talking about time equals infinity. So the inductor looks like a short. And here's our I sub L at infinity. And because time is greater than 0, this U of t turns on. It's a 1 times 10. So this looks like a 10-volt source. And this I sub L of infinity is clearly going to be either positive 10 over 4 or negative 10 over 4. Since this 10 volts tends to push things out the positive side in the same direction as IL of infinity, it's going to be a positive 10 volts over 4 ohms, 5 over 2 amps. And that's the 3rd step. 4th step is to put it all together and to say I sub L is going to be, actually, I don't even need to say I sub L. We just have one current defined here. So I of t, where we know it's the current through the inductor, is equal to I of infinity plus I of 0 minus I of infinity times e to the minus t over tau. So we said I of infinity up here is 5 over 2. And then we're going to add to it 2 minus 5 over 2. So let's see, 2 is equal to 4 over 2 minus 5 over 2 gives us negative 1 over 2 times e to the minus t over 1 over 4. And 1 over 4 is 4t. And so it's this. So this is the current that goes through the inductor for time greater than or equal to 0. Now we've got our 5th step still. And our 5th step says, finally, we're going to find what we're asked to find. All the way back here, we were asked to find we were asked to find originally V sub L. And instead of finding the voltage across the inductor, we found the current through it. So there is no general rule to finding what you are asked to find. You just have to fool around with different ideas. Now, we know this current. If this current was all going through a resistor, it'd be easy to find the voltage across that resistor, but that's not the case. I guess you could figure out for time greater than 0, this is open, so all this current does go through the 4. And since all of it goes through the 4, you could figure out that voltage. It's just whatever I is times 4. It's this mess times 4. And then you could add it to 10 And that would give you V sub L. And that's one perfectly good way to do it. Let me write that one down, and then I'll show you what I think is going to be a faster way. We're going to do the goal again is to find what our V sub L is. And I see there's a loop on the right. And for time greater than 0, the loop on the right gives us plus V sub L. And we can go around here, minus 10, because for time greater than 0, this is a positive 10. And going around, plus whatever this voltage is. I'll call it V sub R. And all that equals 0. And our goal is to find V sub L. So we can solve that for V sub L and say V sub L is equal to 10 minus V sub R. And we know what V sub R is because all this current has to go through that 4 ohm resistor. So V sub R is just going to be whatever I is times that 4 ohm resistor. And we figured out what our I is up here. So we're just going to multiply 4 by this mess. So 4 times this would give us, let's see, 10 minus, right? 4 times 5 over 2 is 10. And 4 times 1/2 is 2. And now we can distribute that out. We get 10 minus 10. Well, the 10 goes away. Minus a negative is positive. So we just get 2 e to the minus 4t. And the units are in volts. So that's one correct way to do it. If you didn't see that, maybe there's a faster way to do it. We want to find V sub L across the inductor. We know I through the inductor. A completely different way is to say we know V sub L, the constitutive relationship for the inductor, is equal to that. So we can find it in one step just by multiplying whatever the inductance is, that's 1 Henry, times the derivative of the current through it. So we're just going to take 5 over 2 minus 1/2 e to the minus 4t and take its derivative. So the derivative of the constant is 0. The derivative of this is minus 4 times a negative 1/2. So that's a positive 2 e to the minus 4t, and that would be volts. And that's the exact same result we got above. So there's lots of ways to skin the cats like this and use whatever you see first. You can kind of see that there's maybe this one took a little bit extra time, but not by much. This probably is the fastest.